Can reality be adjusted after events have occurred? That's the unsettling implication of the delayed choice quantum eraser experiment. We recently talked about the weird results of the single particle double slit experiment. They imply some startling things about the nature of reality. Today, I want to talk about an additional, possibly even stranger version of this experiment, whose results force us to reconsider the nature of causality itself. Now, this episode isn't going to make a lot of sense unless you've seen the first one, so go ahead and watch it if you haven't already. I'll wait right here. Okay, so the single particle double slit experiment suggests that things may not exist as well-defined, even real particles in that strange interim between creation and detection. There's a fuzzy space in which we don't know the particle's location or path. The Copenhagen interpretation would tell us that in this space, a particle is only its wave function, a distribution of possible properties. It's a probability wave that does all the usual wave-like stuff, like making interference patterns, until something happens to collapse it. At that point, the Copenhagen interpretation tells us that a true transition happens between wave and particle. But is that right? And if so, what really causes this transition? Does observation of the particle's location force the universe into settling down and deciding which particular reality we happen to be in? To head off any wild metaphysical giddiness, I want to say right now that there's absolutely no reason to believe that observation by a physicist is better at collapsing wave functions than observation by an electronic detector, or a houseplant for that matter. We'll talk about what observation really means at a later point. But it's still pretty interesting to see what happens if we try to observe the wave function at different points in the double slit experiment. The great mystery of the experiment is that very particle-like things appear to traverse both slits simultaneously, like you might expect of a wave. Physicists love a good mystery, and so have tried very, very hard to peek to see which slit these particles actually travel through before they produce the famous interference pattern. Turns out the universe is onto us. Any experiment that determines unambiguously which slit the particle traverses destroys the interference pattern. Instead, particles land in simple clumps, one for each slit, as though they were traveling as simple particles the whole time. This is even true if you place detectors on the far side of the slits, after the wave-particle thing should have already been interfering with itself. It's like the wave function is collapsing retroactively, as if the universe is saying, okay guys, the human figured out which way you went, no more funny stuff, better pretend like you were particles that whole time. But there's a huge problem with this interpretation. It's impossible to make these measurements without messing up the wave. The interference pattern happens because the waves emerging from each slit are what we call coherent, which is a fancy way of saying that the relationship between the waveforms emerging from the two slits, so the locations of peaks and valleys, is predictable and stays consistent as the waves move forward. This coherence is what allows the waves to produce the interference pattern in the first place. But when you place some device in the path of either wave, you mess with this coherence, and so affect the pattern that reaches the screen. By the way, the double slit experiment where you try to determine which slit is traversed is called a which way experiment. And if the test is done on the far side of the slits, it's called a delayed choice experiment. Physicists hate being outsmarted by the universe, so they've come up with clever ways to measure which way the particle traveled while still preserving coherence. I'm going to talk about the most famous, performed in 1999. This experiment made use of a very special type of crystal that absorbs an incoming photon and creates two new photons, each with half the energy of the original. These new photons are twins of each other. In fact, they're an entangled pair, so fundamentally connected in strange ways that we'll come back to. So, place this crystal in front of the double slit to make coherent entangled pairs of any photons passing through. send one of each pair off to the screen to produce our interference pattern, and use the other to figure out which slit the original photon passed through. Let's focus on detectors A and B here. Detector A lights up if the original photon passed through slit A, and detector B lights up for slit B. If we run this for a bunch of photons, we see that whenever detectors A or B light up, we get a simple pile of photons here at the screen. No interference pattern at all. It's as though any knowledge of which way the original photon travelled stops it from acting like a wave during its passage through the slits. And crazier, this experiment was set up so that photons reach A or B after their twins reach the screen. So, a photon lands on the screen according to the pattern defined by its wave function, and then later, its entangled partner reaches detector A or B and somehow retroactively influences the previous landing position. It's like the second photon is saying, whoa, 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 someone figured out which slit I came through, you better look like you came through that one too. This is amazing, and given that we only interact with one of the entangled pair, surely that means we aren't messing with the other, so we aren't ruining the interference pattern with decoherence. Could it get any weirder? This is quantum mechanics, so yeah. This extra stuff is the quantum eraser. Its job is to destroy any information about the path of the photons. These devices are beam splitters, just half-silvered mirrors. They work by allowing 50% of the photons through while reflecting the other 50%. Now, you have a new possible outcome. Instead of being reflected to detectors A or B, half of the photons end up in detectors C or D. But this clever arrangement ensures that if C or D light up, we have no idea which slit that photon came from. If we only look at the photons whose twins end up at detector C or D, we do see an interference pattern. It looks like the simple act of scrambling the which way information retroactively sends the message, okay, chill, the observer lost the info of which slit we went through, it's safe to have gone through both again. Are we forced to double down on the interpretation that observation of the path causes the collapse of the wave function, and that the wave function can collapse all the way back to wherever our new knowledge extends to in the past? Some sort of retroactive reality cascade? This is a pretty wild story. For that reason, it makes sense to be cautious, even of the Copenhagen interpretation. Part of the appeal of the Copenhagen interpretation is that it avoids any physical interaction that moves faster than light. See, when a spread-out wave function resolves itself into a set of known properties, say the location of a particle on the double-slit screen, somehow the entire wave function knows to do this, to collapse at the same instant. But if these wave functions aren't physical, as the Copenhagen interpretation would tell us, then there's no real instantaneous physical interaction. By contrast, a physical interpretation of the wave function, like the de Broglie-Bohm pilot wave theory, requires an underlying physicality, a set of defined properties that evolves with the wave function, so-called hidden variables. That's a bit uncomfortable, because to explain experimental results, those physical properties need to act and change instantly at any distance. They need to have what we call non-locality. Now, the delayed choice quantum eraser double slit experiment doesn't tell us whether the wave function is physical or not, but it tells us that the Copenhagen or any other metaphysical interpretation of the wave function is no less, well, crazy sounding than a physical interpretation. In fact, the solution may lie in this fascinating phenomenon of quantum entanglement. As we'll see in the future, entangled particles really are able to influence each other instantaneously, and we'll see that their non-locality doesn't violate causality. So perhaps they can even affect coherence and decoherence retroactively and physically without making a causal mess. Perhaps this thing we call observation is just entanglement between the observer and the experiment. Perhaps the evolving tapestry of entanglement, in all its impossible complexity, is what really defines reality in this space-time.